Martin McClure, everybody. And here we go. Martin McClure.
If I can get my microphone to stay on. Well, that's a talent. Okay. So, how many people here have seen me give a talk about MIST, or on video or on in person? There's a few, but not very many. That's kind of what I thought. So, explaining this in 45 minutes so that you actually understand what it's about is a little bit of a push. So, we'll see if we can get through it. Okay. So a lot of you have seen this particular little aphorism that tries to get you to work together nicely. Well, I have a different version of it. There is no C in Smalltalk. Now, it occurred to me several years ago that you really don't actually need to write a virtual machine in C. I mean, once you have JIT technology, I mean, you're creating machine code at runtime, and you're running it at runtime, and you're substituting it at runtime, and you're doing all this stuff. And why can't you just write the jitter in Smalltalk and get rid of the virtual machine altogether? And I said, okay, that's kind of cool that you might be able to do that. But then eventually it started looking like a good idea. And why should Smalltalk depend on some other language? I mean, C doesn't, Forth doesn't. Why should Smalltalk? And that was the birth of the MIST project. Really, when I started the project was when I found that I really wanted to do some experimentation with things like actor model concurrency rather than threaded concurrency and things like that. And I found that I would really need to mess with the virtual machine and the virtual image and the interface between the two, and that just seemed too hard. So I said, well, let's just go ahead and do this thing I've been thinking about, and then that will provide a good experimentation platform for me and hopefully for other people since it's open source. So it is open source, it's MIT licensed. MISTproject.org is the place to go for information. The video of my previous talk is up there. And today I will be zipping through some of the code examples that I go through line by line in that other one, so you may actually want to go and look at that video if I just completely lose you there. Also, there are links to the mailing list and to the code repository, which is on GitHub. So, status is not very far along as far as code goes. What you'll be seeing today is mostly design work, and almost everything I show you is not written yet. So therefore it has bugs, and the design may change before it's actually implemented. But there is some code done, and it does do something. So if it's not done yet, then why talk about it now? And the reason for that is, I want to share the design out, because when I've done this in the past, I get really good design feedback, I get great ideas that I fold in, and hopefully some people will take my ideas and run screaming the other direction, or maybe even adopt them. So, it doesn't matter how it inspires you. If it inspires you, that's great. So I've made some kind of interesting design choices, and so I thought it would be good to share the values of the project that have sort of led me to that. This is kind of what drives it in Rebecca's, X-driven design. If there's anything that is X-driven design in this particular project, it's simplicity-driven design. But these are the list of the values. Let's go through each one very quickly. Self-sufficiency. This is no virtual machine, not written in C, written as much as possible in itself. We don't actually. The core functionality doesn't even load libc. We are dependent only on the Linux kernel. And but we do also want to maximize interoperability. So eventually we will be loading libc, if only to be able to load the dynamic loader in order to load shared libraries and be able to call them. We are, from the very beginning, we are ABI compliant on our stack, discipline, and so forth for calling methods. So it should be pretty easy to call out from MIST into things written in C or other languages, or to create a shared library that is itself a MIST image that has entry points that can be called into. Both of those are things that I would like to see happen. The next value is simplicity. I don't think I have to sell that too hard. Simplicity makes things much easier to deal with, much faster to modify, program, and occasionally even faster at runtime. About simplicity, this quote, everything should be made as simple as possible, but no simpler, often attributed to Einstein. Einstein did actually say something very similar to this, but he said it in a more complicated way. The next value is consistency. You want to have the smallest number of concepts uniformly applied. That concept has been around in Smalltalk for a long time. Avoid exceptions to the rules. As applied to this project, it applies to things like if true, if false, and loops, where the compiler does things that mean that that you can, if you try to override if true in most Smalltalks, you find that it doesn't work. Now, it may be a bad idea to override if true, and I really can't think of a case where you want to do that. On the other hand, if you do it, you don't really want to be puzzled by why it didn't work. So trying to avoid those kinds of things, find different solutions to the problems. We'll talk more about that later. Speed is actually a value. We want to be reasonably fast, at least. Faster is better, of course, but in the same speed class with comparable to other popular Smalltalks. Now, there's tension between the simplicity and the consistency and the speed. We've got to work that balance out over time. The last value, craziness. I added this one since the last talk because I saw this interview with Larry Page, Google CEO, where he says, if you aren't doing some things that are crazy, you're doing the wrong things. Now, this, of course, does not mean that everything you do should be crazy. It means that you should pick some crazy things to do because you can't make quantum leaps forward without doing something crazy. If you just do what's been done before, you will never make a quantum leap forward. Now, many crazy things people do don't lead to quantum leaps forward, but you can't even have a chance of making a quantum leap unless you do something that's crazy. So we're going to try to be somewhat crazy. So that's our values. In order to achieve the values, there's a set of strategies. First one is spend memory freely. We don't want to waste memory, but if I can buy one of my other values, if I can buy simplicity or speed or consistency by spending a little more memory, I'm going to do it. Most of the current implementations of Smalltalk were designed and originally implemented at a time when 10 megabytes of memory was huge for a whole machine to have. Today, even pocket things have a gigabyte. So, and if Thunderbird can eat 200 megabytes of resident set size when I launch it without even looking at any email, I think that I don't have to worry too much about this unless I really try hard to waste memory. Start simple. If there's a simple way and a complicated way to do something, do the simple way first. You can always do the complicated thing later, and test your assumptions. Once the simple thing works, if you think a complicated thing will be, say, faster, then mock it up. Come up with that, test it. See how much faster you think it's going to be, and then see how much complexity that's going to add. See if it's worth it. Maybe it isn't. I don't want something that's twice as complex that only gives me a 10% speed gain. If I can go 15% more complexity to be 3 times as fast, I'm going to do that. Try for broad solutions. When you're faced with a problem, don't just try to solve that problem. Try to see if there's a single solution that solves an entire class of problems. We'll see an example of that later. Do the unconventional thing first. If there's a conventional way to do something and an unconventional way, it looks like there's even a chance that the unconventional way might work better, try it. You already know how the conventional thing is going to work. See how the unconventional thing works. And if you then need to retreat to the conventional way of doing that, do look at the risk. If you really can't afford to redo the whole thing the conventional way, then you should do it the conventional way from the beginning. But at least, think about that. Try doing the unconventional first when you can. And also, shoot for the 80-20. 80-20 rule is not really a rule, but it is true a lot of the time. And if you can get 80% of the benefit of something for 20% of the effort, then that's great. Some people have asked me, why don't you just use LLVM? LLVM is big and complicated, and if I can make something that's 20% the complexity of LLVM, that is 80% as useful in this application, of course there's many things that LLVM is good for beyond this, then that seems like something to go for. So that's the values and the strategy. Let's take a look at the actual design of this. So the initial target is x86-64 on Linux, and it's designed to be able to be extended to other targets. The first time we do extend it to other targets, I'm sure there will be a lot of refactoring because mistakes were made and things were displeased, and that will force us to clean that up, but it is designed for that. And like I said, we just depend on the kernel initially. So the way it works is that MIST code, which is the Smalltalk level code, it compiles to FOG, which is an intermediate form that is a tree of objects that basically is an AST and not a whole lot more. And then the FOG compiles down to machine code. And you still need primitives because ordinary methods can't do things like add two integers together because Smalltalk syntax just knows how to send messages and assign to variables and declare temporary variables. There isn't any syntax for anything else. So primitives you still need. Primitives are written directly in FOG. The way that works is that there are node types in FOG that you cannot get by compiling MIST code. Nodes like add two integers together and if this, then that. And actually you write a MIST program that assembles some nodes because there is not a syntax at this point for FOG. There could be, but I'm not anticipating that enough primitives will actually be needed to be worth doing that. So for now you just write a program in MIST that assembles some nodes and then you compile it to machine code. Primitives are ordinary methods. They just have these different node types, but they execute as an ordinary method because there's no virtual machine, there's no line between the VI and the VM, and therefore there's no concept of failing a primitive and going back up to the high level. If the primitive needs to send a message because some test failed, then it just goes ahead and sends the message from inside the primitive. So what you get after you do one of this and you want to save your image, what you get is you get an executable file. You get an ELF executable that contains all of your objects. And when you launch it, it runs. The kernel just loads it into memory and runs it. And if you want to be able to go to a different platform once we are multi-platform, then you would do a save image as. And it will basically target compile that image and write it out so that it's in whatever format the kernel of the machine you're targeting it for needs in order to load it. Now we do sort of static compilation. Each method is compiled individually, but at the original compile time, when you hit save in your browser, it compiles the machine code. So there is machine code for that, but the method lookup and things are fully dynamic. You get the fully dynamic behavior that we expect. Later versions that are faster and might do inlining will dynamically recompile at runtime. Right now it's static only. Because it's only memory, right? And if there is always a machine code version of a method out there, you can always run it. You don't have to worry about whether your compiler can run, whether you've stripped the machine code out of your compiler code or not, and that sort of thing. So let's look at what an object header looks like in MIST. So, right, to a virtual machine, objects are not polymorphic. All objects are kind of alike. It needs some kind of a common representation for all objects. And that's what an object header is for. It's for communication with the virtual machine. Well, when you don't have a VM, when almost all of the traditional VM functions are handled up at the high-level language level, then you can do those by just sending messages and have fully polymorphism. So you don't need an object header. But you still do need the state that's in the object header. You need to know what class that object is. You need to know its identity hash, things like that. But we have a mechanism for doing that. They're called instance variables. So all those things like whether it's marked or not and its class and things, these are instance variables of the object. The only real restriction is that the word pointed to by the object pointer in memory must contain the class of the object. Where the rest of that instance's memory is entirely up to the instance itself. Now in most cases it will be the first word. The only real exception that I'm planning for the early part is the stack object, which because it is a hardware stack, it grows from high addresses to low addresses. And therefore, the fixed instance variables will be very near the end of that object. And therefore, it needs to override a number of methods in order to be able to handle that. So, you probably, at this point, need to get some idea of how this actually looks. So let's take some actual examples. So let's look at memory management. So first thing is the objects never move in memory once they're allocated. They stay at the same virtual address. forever. There's no compaction. This simplifies things in a couple of different ways. You don't have to write a compactor. You don't have to worry about compacting the code that's running the compactor. And the native code of each compiled method is actually in the compiled method object. And that contains send-site caches, which refer directly to addresses of other methods. And if they don't move, that makes that a whole lot easier to do. The problem with non-compacting garbage collector is that in the past has been that you can get fragmentation. And to minimize fragmentation, we use exponential allocation. So there's only 8 sizes of objects in the heap. Each one's twice as big as the last. We have a 64-byte object, 128, 256, and so on, up to 8K of objects. Anything bigger than 8K is allocated in multiples of page sizes directly. It's then mapped directly on the heap, or directly from the kernel, and then returned to the operating system when it's not. Otherwise, you have this structure called the object manager, an instance of object manager, which maintains linked lists of all of these objects, each of which is a class free space. And that's all the free objects in your system. There's no free memory in the system. There are only, every byte of memory in the entire thing is in some object. So let's look at some of the code very quickly, like I said. Okay, so this is your, this is basic new, and it asks the class, well, what physical size should your instances be? And there's some other wrinkles when you get to index instance variables that I've left out in the interest of time, but I've got it worked out. And then it says, well, object manager, get me one of those, and then tell it to initialize itself as an instance of me, which does things like nil out the instance variables and then change the class to be the class that it's doing, and then sending initialize to that guy, and then returns it. That's fairly simple. And this is this just pulls the thing off the right, off of the right list. And then if there isn't a list, it says allocate the ours object, which is that mmap that I talked about. And then if it can't find one, if the queue is empty, then it does this allocate object of size. And what that thing does, I'm not going to show you the code for that, but like this is an empty list here for 512-byte objects. If you wanted a 512-byte object, it would say, oh, that's empty. So I'm going to go here and grab a 1024-byte object. I'm going to split it in two, make 2 512-byte objects out of it, put those on the list, and then return the first one of those. And if it goes all the way out here and it finds that it's out of 8K objects, then it has a choice to make. It can either allocate some memory from the operating system, break it up into 8K chunks, and put them all on this list on the far end, and then work from there. Or it can try to run a garbage collection to see if it can make new objects. It keeps an allocation count to see how many objects it's allocated since the last time it garbage collected, to have a heuristic of which one of those strategies it should try. So garbage collection. There are 2 messages that every object must understand. GC mark says, well, if I am GC marked, if I'm not GC marked, then do nothing. Or if I am GC marked, do nothing. If I'm not GC marked, then set my mark to true. So this is just an instance variable, would normally be in the header. And then self all references do send GC mark. And it's up to the object to know which things in it are references and which things might be bytes, because all byte objects have object references and bytes in them, as we all know, but in a traditional implementation, the object references are all in the header. Since there's no header, we have to deal with mixed things. But the classes have to know how to deal with that, which turns out to be not that hard, except in the case of where there's index instance variables, and especially if you have multiple sets of index instance variables, which is technically possible, but I don't really recommend going there. And then once you've marked everything that needs to be marked, then the object space objects go linearly through memory, sending every object GC sweep. And that says, well, if I am GC marked, then I'm alive, and I just set my GC mark back to false. Done. If false, then I'm garbage. And so I basically set my class to free space and put myself on the correct free space list. And free space implements these 2 methods to do nothing. And this is just the code for adding something to the list. Or if it's a large object, it maps it right there. So I haven't shown you scanning the stack for references and a few other things. I've shown you about 35 lines of code. I expect that all of memory management will come in at maybe 100 lines of code. If it reaches 200, I'll be really surprised. So let's see how method lookup works. Kind of. All right, this is assembly code. This is what's inside of every send site in a compiled method. And I'm not going to go through this line by line. Look at the previous video if you need to see that. But basically, it says, well, is the receiver a small integer? If it is, it knows where to go. Otherwise, this thing in blue is a monomorphic inline cache. And if that hits, then it knows where to go. And if it doesn't, it goes to this cache miscode, and I'm going to basically scroll this up. That's the end of the monomorphic inline cache that we saw before. And it sets up some parameters, and it makes a message sound to this. It's a method dictionary cache miss app, and it's sending that to a selector-specific method dictionary. So method dictionaries in MIST are set up a little bit sideways from most Smalltalks. A message send is keyed on two things: the class of the receiver and the selector that you're sending. In most Smalltalks, you find by the class of the receiver, you find the dictionary to look up, and then by that there's a dictionary that's keyed by the selector. We do it the other way around here. The selector is known at compile time. Therefore, we have a dictionary that is keyed by receiver class for that selector. The address of that dictionary is compiled in as a constant, and it is that object to which this message is sent. So now we're doing a full method lookup at the high level while we're in the middle of a cache miss. So we obviously can't afford a cache miss there. So you have to make sure that your inline caches in that little bit of code, that they are never invalid. And that actually turns out to be relatively easy because almost all of the sends in there are either self-sends or sends to small integers. But that's really why the monomorphic inline caches are there, because it would be simpler without it. And let's do the simple thing first, right? That here, I didn't really want to have to write method lookup twice. So that's message sending. Let's take a look at loops and conditionals, how that works. So conditionals, Dan Ingles earlier said that this was like one of his favorite things about Smalltalk, is that there is no actual if at the bottom of the if. It's just message dispatch takes care of it for you. And even though the compiler normally optimizes this in most Smalltalks, this code will work as written. So that's the way we'll do it. It's simple. Now loops are another story. How do you write a loop in Smalltalk? Well, when I looked at it in Smalltalk 80, it's written recursively because there's no way to actually do a loop in Smalltalk, right? Because it's all this linear flow of send message, send message, send message, return. But you can do it recursively. So here's an implementation of 2by-do, and this method just figures out which direction you're going and makes sure that you have to execute the block at least once. And then it goes into the recursive routine, which simply says evaluate the block, increment the index, and then see if we're over the limit. And if we're not, call yourself, which will do the same thing. Now, of course, this works. But as I found when I executed a very long loop in Smalltalk 80 in 1985, I didn't run out of memory, and I didn't understand why not, because I could see that this was the implementation or something kind of like this. And of course, the compiler cheated. Well, I don't want to do that cheat. I want to do a different cheat. But I don't want my stack to get 10 million deep when I run a benchmark. So, broad solution for the entire class of problem, let's do tail call elimination. That means that everything that's recursive, that's tail recursive, will be flattened out and won't use stack. It might be a little faster. So the way we do that, this is what happens at the end of a normal method. This is like the last message sent in the method, and then we deallocate any temporaries that we had on the stack, and then we return. And so what we do instead is everywhere that you would have called to another message within this message send, if the last thing in the method is a message send and it qualifies, which most things do, I won't get into the details right now, is you deallocate first and then you jump instead of call. And that gets you to the next method. Let's take a look how that works in our loop. So here is our first method, and the last message send in this method is the send of if false. So that becomes a jump to if false. And then the if false, the last message send of that is sending value for the block. Now, a block in Squeak or squeak, in Mist, is every source code block creates an anonymous closure class, which has one method. And so in this case, the method is value, because it's a niladic block. And so that one, the last message sent in that is this to by positive do, which becomes a jump instead of a call, and it takes us back to where we were before. So we go around and around these three things, and the stack doesn't get any deeper. Now, performance probably isn't all that great. Once we get to inlining, hopefully that will fix that. It'll be some time from now. All right, so everything I've showed you so far is fairly unconventional, but it's not actually crazy. And we said craziness was a value. So it's pretty clear that that stuff's going to work. I mean, the performance in the really simple version, they get really bad. The garbage collector is expected to get really slow if you get very big, for instance, and we'll have to replace it with something a little more complicated. But, okay, so what's actually crazy about this project? So how many people here are familiar with traits? A fair number, not everyone. So let's go through really quickly. A trait is a set of methods that none of which access an instance variable, and they provide methods to classes. You can compose traits into your class and then add your own methods and instance variables. So and it's a very nice way to organize things. They provide methods to the classes, and then they also, anything they do that's a self-send within their methods that they don't implement becomes a requirement that the class that they're composed into provide those methods. And often those are accessors to instance variables because they can't have instance variables. And traits compose together, and which just basically means that when you compose traits together, you get a trait that consists of all of the methods that were in either of the traits. And when you do that, if they have the same selector, then you get a conflict. So conflicts, there's no automatic conflict resolution. And Nathaniel's thesis that I showed you the title page of goes in great detail into why that's a good thing, that there's no, you don't do it in order of the first one you list, and because maybe you want this one from this one and that one from that one. And so there's some sort of like a little expression syntax that you can use to specify the resolution. You can do things like rename methods to something else, rename the selector. You can omit selectors entirely in order to get to the point where you have no conflict. Well, for Mist, I actually wanted traits, but I wanted them to actually have state. I wanted them to have instance variables that went along with them. Here's a very simple example of a trait that I might like to have. Once again, this is an example that would be in the virtual machine and the object header in most cases. So it's a trait called identity hash, and it has an instance variable called identity hash that it adds to any object that uses this trait. And it says, here's a method, identity hash, and says, well, if it's nil, then set it to a random number and just return it. And so that's a very minimal trait, but it's a useful trait to have. And it's nice to split those things out. Another thing that I thought would be nice in Mist is to make indexed instance variables a trait. So you get this trait and you get the memory for the indexed instance variables, and you also get the methods like basic at and basic at put. And if you don't have this trait in, you don't have indexed instance variables, and if you try to send basic at or basic at put to this object, it says message not understood, because it's a meaningless message to that object. Unlike in most Smalltalk implementations where you send that and it just says, sorry, you're not indexed, but the message is actually there. You can ask, do you understand at or basic at? You say, oh yes, I understand that. But then you actually try it, it doesn't work. So then, after I gave my talk in Argentina last November, I was walking through a park in Buenos Aires with Andres Balud, and we were talking about Mist, and he said, traits with state and classes are awfully similar. Do you really need both concepts? So on the 10-hour plane ride to Miami that night, I started seeing if I could smush those together and eliminate the duplicate concepts between them. And I had to make a design decision in the middle of that because I realized that I had to choose between whether I was going to support white box reuse, like Smalltalk, or black box reuse, where things are more hidden. And partly in the spirit of do the unconventional first, I chose black box reuse, and that drove some design decisions. So what I came up with is is classes that compose together, like traits compose together, but they do not inherit. There's no inheritance in this scheme. Now, what I'm about to describe could be thought of as a form of multiple inheritance. It's useful for some of the things that multiple inheritance is used for, but I find it much more useful to think of it as that there is no inheritance at all, that you're just composing classes together. So when you compose classes together, what happens to the methods? Well, just as in composing traits, all the methods get added together. You have to deal with any conflicts and rename or omit them. You can also declare methods private when you compose them, because just because the class you're composing from wants to make that a public method doesn't mean that you and your composite class need to make that a public method. If you make it private, then only self-sends, syntactic self-sends, will actually find that method. There is no such thing as a supersend because there's no such thing as a superclass. So we've eliminated that weird little rule about supersends from the language. On the other hand, we've added another weird little rule about self-sends. Another one, since this is black box reuse, if you take a class and compose it into your class, then its syntactic self-sends, if it implements that message, then that goes to that method, always. And because if you renamed that, for instance, you don't want it going through your renaming thing, because that could just totally break it. In a white box reuse situation, that's pretty reasonable. In a black box situation, you really don't want that. So we'll see how this works. It's kind of weird, but then on the other hand, we've eliminated the weirdness of supersend, so maybe we're in conservation of weirdness mode. So instance variables. What happens to instance variables? Well, you get all the instance variables of all the classes that you compose together. Now, instance variables are private to the class that defines them. So only those methods can access those instance variables directly. And methods in that class can only refer directly to instance variables that class defines. So if I compose from this and I compose from that and it has instance variables, my methods in my own class cannot directly access those instance variables. One of the advantages of that is that name conflicts between instance variables are impossible. Well, as long as the individual class doesn't have duplicate names, which is forbidden, then you cannot introduce a conflict when you compose. And as I've indicated before, when you have indexed instance variables, you have to do some extra fussing, but I think I've worked that out. And no time to go into that today. Meta classes compose at the same time as the classes. So the class and instance sides compose together. So class instance variables work the same way that instance variables work. So we have sort of a new idea of what an abstract class is in NIST, because if class is abstract, it actually doesn't understand basic new because you have not composed in the thing that implements basic new. And that same thing that implements basic new also implements the class instance variable. So even if you found a way to instantiate it, which you can't, there's no virtual machine that is willing to instantiate anything that's a class. Even if you could instantiate it, then the class instance variable is not present, so it wouldn't know what class it was, so you couldn't send it a message. But abstract classes are very useful, like that instance or the identity hash class. That's an abstract class. Now, a concrete class is you compose one concrete class into your class, and you have a concrete class. And that concrete class will define the class instance variable, and it will define the things like basic new and things like that. And but you can only compose in one concrete class. So I think you're going to see the style of coding in this is there are going to be a lot of abstract classes. And then when you really want to use them and instantiate them, you make a concrete class. And so you can this is almost single inheritance because you can, a little like single inheritance because you can only compose one concrete class, but many abstract classes. The reason you can't compose more than one is you'd end up with more than one class variable. And it would get very confusing as to what the behavior of this thing was if it thought it was a member of more than one class. And that was too crazy for me, at least at this point. So we're talking about composing classes now. In the Gang of Four Patterns book, they talk about white box reuse versus black box reuse, and object composition as a pattern. And where you instead of subclassing from set, you actually hang on to a set and use its functionality. With class composition, you also have that same kind of trade-off. So where do you use class composition versus object composition? And there are some cases where you have to use class composition, and that's one of the reasons that I included it. And one of those is, at the low level, garbage collection must be the responsibility of every object. Every object has to take charge of its own memory. There are ways of doing it, but where do you put the thing that manages the memory for an object if it's an object and everything is an object? So I quickly came to, well, it has to do it itself. And that functionality resides in a class. So I wanted to be able to compose that into the same object so that it could take care of all the rest of the memory of the object as well. That seemed reasonable. But there are many cases where you don't have to use class composition. In most of those cases, I think that object composition is probably the better answer. The exception to that is when, where if you want to have, if you were using object composition and you were going to hang on to a set and you were going to hang on to a logging object, but your object wants to expose most of the set API and most of the logging API publicly, then in Smalltalk and in an object composition world, you would have to put pass-through methods for every one of those public API methods. And it's much simpler in that kind of case to use class composition. So there are a couple of times where you want to do that. OK, what else have we got that's crazy? There are modules, and I'll be talking to the ModTalk people about that. I'm not going to talk too much about the design of that because it's not very complete yet. What kinds of variables do we have in NIST? There are args and temps. Both method args and temps and block args and temps are exactly the same as in Smalltalk. No reason to change those. The scope is the block or the method, and blocks can refer to things from the enclosing scope and that sort of thing. Just like in Smalltalk, that hasn't changed at all. Instance variables we've talked about. They're private to the defining class. Methods of the defining class, and they are public to. They are private also to the object itself, unlike Dart and Java, where it's code-based. Where a private thing is code-based. It is encapsulated in the instance. In all cases, whether declared private or public. We have module variables, which are most class names, for instance, are module variables. And these things are not intended to be incredibly variable. Most of the patterns I've seen that are actually very useful, they are really constants or read almost entirely. Class names and maybe some root objects would go in there. You can have access to the module variables of all of the module variables of the module that your method is in, and also the variables of any module that your module declares as an immediate requirement or prerequisite. And once again, when you do that, when you declare a prerequisite or whatever, you can rename or omit variables so that they won't be seen from within your module. Class variables, I'm thinking probably not. The main pattern I've seen, you can use class instance variables for a lot of interesting things and send messages to the classes and get the values of those returned and that sort of thing. But actual class variables, the main remaining reason for those that I can see is constants. So I'm tempted to put in some kind of compile time constant that where you can actually at compile time execute a bit of code that returns some kind of object that is basically stored in the method as a literal, as if it were a literal, but it's a more complicated object than that. And then you can just have that method will then just return that constant object that was compiled in. So safety. Now, one of the nice things about Smalltalk, one of its strengths is that, it's very flexible and it's accessible, and this is flexible and accessible as well, even more accessible probably, but it is safe. In Smalltalk, you can't access off the ends of arrays, and and the memory is safe and all of that stuff, but when you put all of the functions that were in the virtual machine, and when you put them up at the language level, then now you've exposed some dangerous stuff. And it might be kind of nice to have that safety back. It's both nice to be able to get in there, but it's nice to be able to actually have the safety as well. So there's a couple of ways that I'm trying to move towards being able to build a safe environment. It might be nice to even be able to accept untrusted code over the network and run it in a sandbox and not worry that it's going to kill you. So, there's some of the privacy things I've talked about. And there's also this not super well-defined concept right now called teams, where a method can belong to a team. And for instance, a team can be the memory management team. And those GCMark and GCSweep methods that every object must understand, you can't, when every object understands GCSweep, which says, if you're not marked, throw yourself on the free object list and change your class to free space. And most objects are not marked, except during garbage collection. So this is, a kind of dangerous operation. So you take something like that and you say, this method is private to the garbage collection or the memory management team. And then it's the garbage collection methods that are on that team that are in other classes and maybe even another package or module, but they're allowed to send that message and nobody else is. So some kind of safety things there. And I think that I have a design for that. The message send design that we saw earlier basically allows for there to be space cost in order to do that, but not necessarily time cost, other than the time just spent because memory is bigger. So what else we have? Not a whole lot. We're massively single-threaded, which is a nonsense phrase that I use to emphasize the fact that right now there really, really is only one thread. Really, only one. Now, the goal is, remember the original impetus for this was I wanted to play with actor model concurrency. So that will be the thing that's added on later, but the initial version really only has one thread. Now, this has implications for debugging, because in debugging what you do is you suspend the thread and then another thread looks at it and manipulates it. Well, when there's only one thread, you have trouble doing that. So the debugger actually is going to be done the way GDB is done, by using kernel calls to stop a process, go through its memory, figure out what's going on, and add breakpoints and that sort of thing. It also does mean that the debugger will actually be able to single step by individual machine instruction. So that should be fun. No string literals. You hardly ever use the ability to randomly access a string. And how often do you really use that? I mean, there will be strings, but no string literals. So what do we have instead? We have stream literals. And you can do string interpolation because of that. When you stream over this, when you finally actually execute it, you say name, colon, and then it just executes this block and inserts the result of that into the stream. And address, and this block, gets streamed into it, and then you can stream that out over a socket or onto a file descriptor or whatever. And it's all X-streams based. And it would also be nice to get something like that for input as well, something that you could use for both lexing and parsing, something like regular expressions except more powerful and not as ugly. Haven't come up with that yet, still would like to. Okay, why am I doing this? I'm almost out of time, and hopefully you've got the idea of that anyway. I'm learning a lot, and hopefully this will make a good experimentation and development environment as well. So where are we right now? Right now, the FOG compiler compiles to machine code. We can write an ELF file, and that ELF file will execute. What is actually executing today is basically kind of fat single primitives as a program, nothing object-oriented yet. We're getting very close to the point where the first message will be sent, which will, of course, be 3 plus 4. And that's it. Thank you. Yes. I will be around tonight and tomorrow for questions. Do we have time for questions now? Any? Maybe one. Richard?
But you talked about methods in a team only being callable by other methods in the same team.
Yes.
How do you cross that boundary? How do you call the first one?
Oh, well, the first one may not be, no, if it